Just in case, Timothy, if you didn't know, the AVSO's annual meeting is just going to be over in Huntsville this coming year, so in early November. So if you're interested in meeting people in person and going to one of AVSO's annual meetings, great place to be. It's going to be at the U.S. Space and Rocket Center in Huntsville, Alabama. So not only will you get to enjoy a really cool museum, but they have a full-scale Saturn V sitting on its side, disassembled. One of the coolest places I've ever been. So make sure you check it out. Let's see, Tim's asking on a weekend. So I'll go ahead and I'll paste the link to the meeting in the chat, but it's at aavso.org/113. So we haven't opened registration yet, but just a few details are posted there. It's going to be on November 8 through 10, which I believe is over the weekend. Yeah, it's Friday is kind of our standard opening reception. 9 and 10, Saturday and Sunday are the two other days. So hopefully we'll be able to see you there in Huntsville.
Great. Thanks for sharing those details, Brian. It looks like we're at 2 p.m. Eastern time now, so I think we should go ahead and get started. So first, I'd just like to say hello and welcome, everyone. My name is Lauren Herrington, and I have the great pleasure of being your host for today's webinar. Joining me, we have 3 talented AAVSO section leaders, and they each have something special to share about each of their sections. But before we dive into that, I do have a few quick announcements to make. First, just a little orientation for using Zoom here in webinar mode. As you've been introducing yourselves with the chat box down at the bottom of your screen, you may have also noticed a button next to it labeled Q&A. That is the most important button on your screen. When you click on the Q&A button, you will be able to type in questions for any of our presenters. You can type in questions at any point during the webinar and submit them at any time. Don't worry, it won't interrupt the presentation. After everyone has had a chance to present today, we will have about 30 minutes set aside to answer questions, and we'll do our best to get to each and every one. There's another button down there labeled CC, or Show Captions. If you click on that one, you can enable or disable Zoom's automatic closed captioning, which can be amusing or distracting. I'll let you decide which it is. Now, today's webinar is the first in an exciting mini-series, which we are running this month. It's called Sections in the Spotlight, and it features the leaders of all of our AAVSO sections, which you'll be hearing about more in a moment. Registration is open for the rest of this month's webinars, and you can sign up by going to aavso.org/webinars. You can also view the schedule there and read a bit more about the upcoming sections. The next webinar this month will be next Saturday. That'll be June 8th, and it will feature the exoplanet section, the YSO section, and the INE section. That's Young Stellar Objects and Instrumentation and Equipment. I hope to see you there. Now, I would like to thank our 2024 series sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. All right. It is almost time to hear from our section leaders, but before we do, I'd like to give a little bit of context, just for those of you who may not be familiar with the AAVSO's section system. Let me go ahead and get up these other slides here. All right, we'll begin with the essential context, and that is the AAVSO and what it is. So for those of you who are new to the organization, the mission of the AAVSO is to enable anyone, anywhere, to participate in scientific discovery through variable star astronomy. We do this in a lot of different ways. We have a diverse group of participants coming from all sorts of backgrounds at all ages, from high schoolers to retired career professionals who used to be astronomers in their day job. I personally joined as a high schooler a couple years ago. We're all united by one thing, and that is that we are all interested in astronomy and scientific astronomy in particular. We want to contribute. We want to have an impact. Now, being such a large organization, we do have a wide range of capabilities and instruments which are represented among our observers. We welcome everyone from any background. So some people join us in order to receive education and training in astronomy and variable star studies in particular. Some others are working with professional astronomers, and a few people, we estimate about 2 to 10% of our participants, are actually conducting their own independent research projects, with publications resulting from that. Among our observers, we have a huge range in instruments being used. We have people who observe just with their naked eyes and make variable star estimates that way. We also have people using inexpensive DSLR cameras, and people with more traditional CCD or CMOS camera setups. You can use anything from just your eyes or just a bare camera to a meter class telescope. You can see a picture down there on the bottom right of one of our observers with his 0.8 meter telescope. And we have a large variety of modes of observing. That's part of why we're going to be spotlighting the sections here. So we have people who are not only doing those naked eye estimates or the CCD differential photometry type. We also have people who use classic photometers or spectrographs for our spectroscopic database, speckle cameras, and of course, there's a wide variety of software which has been developed to support our mission. Right. So to take a look at AAVSO's statistics, some things that I want to highlight here are that we have 1,200 members right now, thereabouts, 800 observers, and 200 volunteers. These people are spread out all over the globe. Of course, as we saw during the introductions phase of today's webinar, we have people tuning in from all over, and we're so grateful for all of you. We have 6 staff members and 3 contractors and a budget of about $1 million per year. So, that tells you something about the size of the organization. We do education and public outreach through this webinar series, but we also have a lot of other educational resources, which you can find primarily on our website. We have a mentorship program. So those people who join the AAVSO get access to experienced mentors who can teach them all about their preferred mode of variable star observing. And we run choice courses annually to give people the opportunity to learn more specialized topics. We had one that just opened a couple days ago, which is about data quality best practices. That's one that should be pretty promising. Our data is used in a large number of publications per year, about 380 publications. And this data comes from our selection of databases. So we have a photometric database, we have a spectroscopic database, we have one dedicated solely to collecting exoplanet transits, and another just for cataloging all of the variable stars that are out there. Now that one is quite a standard in the field. And of course, as Brian was talking about at the beginning, we do have our annual meeting. Next one coming up in Huntsville, seems pretty exciting. And other workshops and activities that we hold regularly. So that's the AAVSO. Of course, as I stated at the beginning, our mission is to enable anyone, anywhere, to participate in scientific discovery through variable star astronomy. One of the primary ways that we do that is through our sections. So when I first joined the AAVSO a little while back, I heard about the sections, and my first question was, what is that? That's kind of a vague term, right? The word section could mean a lot of things. Well, now that I've learned more, I found out section is really just code for special interest groups. So if you're familiar with special interest groups from astronomy clubs, say, this is very similar. Each of our sections is a group of like-minded individuals who are focused on observing and recording data for one particular class of objects, or possibly to using a particular type of observing. We have the spectroscopy section, excuse me. And that one is people who like to observe all types of variable stars using spectra. Or we have the eclipsing binary section, which we'll be hearing from today. That's people who are dedicated to observing eclipsing binaries, whatever their observing mode. Our sections are organized into a group of members and overseen by section leaders and science advisors. It's pretty much what it sounds like. The section leaders steer the section, decide on their activities, and the science advisors are on call to provide professional input whenever it's needed. Sections are open to anyone. You don't have to officially be a member of the AAVSO to participate. Right now, there's several different ways to participate in sections. There's regular monthly meetings run by some sections. There are forums, there are email groups. So there's two pieces of advice I can give if you want to get involved with the section. We'll cover more about this later. First is go ahead and just reach out to the leader of the section that you're interested in. When you visit our website and view the list of sections, you can click on one. It'll say right at the top who the leaders are, and it'll have a contact link next to their name. Go ahead and just click on that contact link, reach out and say that you want to get involved. You can also visit the URL shown on the screen, aavso.org/join-a-section. And on that URL, you'll find instructions for joining a sections forum. This is one thing that's universal to all sections. And so it's a good way to stay up to date with the ongoings. All right, so there's some background about the AAVSO, its purpose, and our sections. Now, I'd like to hand the floor over to one of our section leaders so that we can hear from them about what their section is working on. So I think to start off, we will go to Mike. So Mike, I'm going to go ahead and end my screen share here. And we'll hear from Mike Soukup, who is the leader of the long period variables section.
First of all, let me say good morning, good afternoon, good evening or depending on the part of the world you live in, for joining all of us in this webinar. I'm now going to turn on my slideshow here and see if I can get this going. And okay. First of all, let me just start out by calling your attention to what looks like a blue shaded comet as the LPV graphic or logo. So, what is this? What's this got to do with LPVs? Well, it's just my version of an LPV. The multi-shaded blue ball there just kind of shows in a very graphical way, artistic way, pulsations of the star. And the tail off to the left really represents mass outflow from the star. Most of the objects that we observe, really all of them, exhibit significant outward mass flow. And in ways we don't quite understand, that mass outflow does affect the light curves of the stars and is manifested by whatever changes are going on inside the star. So much for that. Okay, well, as Lauren pointed out, mentioned, I'm the leader, and as the leader, I have to spend a minute at least talking about myself. I've been an amateur astronomer since I was a kid back in the 60s, a very long time ago. And I've been an amateur really off and on since then. And I've also worked at several professional observatories over the years. And I've been an AAVSO member for something like 27 years. And I've been an on again and off again observer. Most of the objects I've looked at have been LPVs. I've not really tried my hand at the other many types of variables that you're going to hear about in this series. And I started out, like many, as a visual observer with a small telescope. And I mostly these days do CCD photometry of different types of LPVs. My section is backed up by two super capable science advisors. John Percy has been associated with the AAVSO for decades. He was a professor, I believe, at the University of Toronto. and he has mentored many, many people, high school students, college students, AAVSO members, you name it, for decades. He published an awful lot in our journal, and he's retired from being a professor, I believe, but he would like to continue work with us as a science advisor, which is great. Joyce Guzik is another person. I do know Joyce personally for about 30 years. She knows an incredible amount about pulsating variable stars as well. Um, Her angle is more from the theoretical modeling side, but she has been working with the AAVSO for quite a few years and has been on the council and so forth. Um, so all the things that I don't know, these two people do, or pretty likely. Okay, very quickly, this is what I want to cover today. This is just an overview. It's an introduction to the LPV section. I'm going to talk a little bit about what is an LPV, the different types or classes. It's very broad brush. I'm going to have a few words to say about, okay, if you're interested in observing them, maybe you already are, but I want to talk about what are the pros and cons of picking LPVs to look at, and the instrumentation that you could use to observe them. I want to say a few words about projects. All the sections have been asked to think about projects within their sections. And these would be projects which if they pan out successfully, we would publish papers on the work and the result. And then the last topic is really communications between the members of the LPV section, and that would bring me to a close. So here we go. So what is an LPV? The great majority of them are low mass objects, and they're at the pretty much the ends of their lives. These are generally, most of them start life as around a solar mass, a couple of solar masses. They lose mass as they evolve. And so many of them, by the time they get to be an LPV, they're something less than a low mass, one solar mass object due to stellar winds. And then they, as I'll show you in a moment, they get to a stage of the evolution. This would be to the right or the cool side of the Hertzsprung-Russell diagram. And that's where they do their thing that we observe, which are pulsations. Again, most of them low mass, and most of them are cool stars by the time we get around to observing them. These are basically red giants, red supergiants, yellow supergiants, and we do have a few yellow supergiants, massive yellow supergiants, and some blue ones. These exhibit long period variability. They are typically 10 and above solar masses when they start out their lives. And again, they're not very common, but they seem to be increasingly important to study as LPVs. If you had to put a range of periods on what an LPV is defined as, I'm going to say tens of days. These would be RV Tauri stars, which are very late in life yellow supergiants. These are on the asymptotic giant branch, we think, and about to turn off as post-AGB objects on their way to becoming white dwarfs. Most of our red supergiants are Myra-type stars and semi-regulars, whatnot. These typically have periods of hundreds of days. Myra, which is probably the most well-known LPV red giant, I think has a period of 360 days, something like that. And some of them do have very long periods, and these are typically massive red supergiants. These are Betelgeuse is a pretty good example. of one of these red supergiants. There are a number of others, but they tend to have very long periods. And so what is physically the cause of the pulsations that result in the light curves that we observe? Generally radial pulsations. And for the most part, changes in the opacity in the outer layers of the star cause these radial pulsations. But as you get particularly into the red part of the HRD, which is where most of our stars are, convection and mass loss almost certainly play major roles. And there's an awful lot that still is unknown about that, and which is why it's very important to keep on observing these things. We're going to try to learn what we can about what's really going on inside the star by continuing to build a lot of data on it, on their photometric behavior and spectroscopic behavior.
Hey, Mike, you've got about 2 minutes.
Oh, I'm going to have to go fast here. Yep. Take a quick look at this side. This is essentially what we do. We support the AAVSO mission, as Lauren just told you, and the duties and responsibilities are pretty much listed here. And this is really true for all the sections. I want to show you very quickly the HRD diagrams. My goal here is to show you that most of our stars we watch are typically over in the cool end of the effective temperature. I have HRD diagrams, HR diagrams of a 1 solar mass and a 5 solar mass star that I just picked at random just to show you that there are some differences between depending on the mass. But most of our stars are on the red giant branch, the asymptotic giant branch, and then on the asymptotic giant branch over in what we call the Cepheid instability strip. You can't do this without a light curve. You can't do this briefing. This is a light curve for Myra, a basically regular pulsating giant. And you can see from the curve here, it's more or less regular, not perfectly so. But this is what an irregular red giant looks like. These have no established defined periodicity, but they do classify as long period variables. One of my favorite LPVs are the RV Tauri stars. These are pretty aged stars. They're on the asymptotic giant branch, we believe. And they exhibit interesting photometric behavior. You have alternating minima as the pulsational cycle continues. You can see that you have a deep minimum followed by a shallower minimum. They climb back up to maximum and then they sink down to another deep minimum and so on. And why they do this is still unknown. A lot of interesting theories, including chaos dynamics and so on. Why do you want to observe them? Well, what we do is generate data from the light curves, and this information is critical to a kind of a science called astroseismology, which what we want to do is to try to learn through the light curve data, spectroscopic analysis, and so forth, what's really going on inside the star. This tells us an awful lot about how they evolve. It takes a lot of observations over years, but we can detect changes in the light curves. Again, it takes quite a while. These stars don't evolve real fast. And occasionally we do find some abrupt changes, and these are interesting. For example, in red giant Myra type stars, occasionally we see bumps in the light curve. We don't know what causes that. Bottom line is we still need lots and lots of data. And you guys, the observers, are the ones that are very key here. The more data we have, the more we're going to understand. Okay, great targets for visual observers when you want to observe them. Many of them are bright. The brightness amplitudes are often big. Sometimes when they're at the minimum, You may not be able to see them with your size telescope. They can get quite faint. On the other hand, most of them can be followed throughout their curve, many of the ones we watch. And so they're great targets. If you're a visual observer, they're right, they're just right for you. And you don't have to observe them every night. Some, as you'll see in some of the sections that will be doing their presentation soon, you've got to be pretty much on the ball. You got to be really dedicated and possibly be outside with your instrument every night, every clear night you can. We, on the other hand, our variables are slow. They don't change real fast in time. So you only need to get out maybe once a week or so, 10 days, and so on. Cons, again, going back, need lots of observations because they don't vary very quickly. The Purkinje effect is our eyes in the red spectrum that we're typically looking at when we see these stars, observe these stars. The eye is affected by the red color, and we tend to overestimate the brightness for that. And it's something when you're doing your observations visually, you need to kind of watch out for or be aware of. Membership. There is no real formal membership. It's really participation. You don't have to fill out an application. You don't have to pay any money. You don't have to do anything other than participate. You can observe, submit data, ask and answer questions, help others. I urge you to try your hand at data analysis and mining because with the slow changes these stars exhibit, only by going back and looking at how the star has behaved over the years do you get a better handle on what's really going on. The LPV forum is our primary communication vehicle. Join that forum. It's really easy to do. You're also welcome to use email. My email is listed right here on this slide. But in general, try the forum. I think you'll find that gives you our best results. I'm hoping to use section webinars 3-4 times a year. We had our first one, which was a learning experience back in February, and we can schedule online meetings as desired, special topics, maybe presentations from the science advisors, etc. I will say very quickly, and I'll conclude, I've been asked a couple of times, gee, what happened to the LPV circular? I vaguely remember the circular from many, many years ago. It kind of disappeared. I didn't think about anything about it. So initially I told people, I said, well, there is no LPV circular. It turns out there is. It's still being published. You have to ask somebody at headquarters to be put on the list. But my personal opinion is I think they'll probably do away with that. And I would urge you to use the target tool that we have on AAVSO. It gives you the same information as but more. And we used to have a max min publication. Max min of the light curves of the variables. We haven't done that in a number of years. It just got to be too much of a problem for people to keep current. That's I overstepped my time. That is me. I'm not known for being succinct, but I thank you for tuning in, and I'm going to give it back to Lauren.
All right. Thank you so much, Mike. Cool. Okay. And just to add a little bit of clarification for people in the audience, the webinars, the section webinars, which Mike just mentioned that his group is running, are really awesome. They are separate from this webinar series. They're a whole nother thing that you go register for on our calendar that you can find at aavso.org/programs-events, and probably also on the LPV webpage. So before I go to the next speaker, Brian, I was wondering if you could add a little something about the LPV circular, maybe?
Yeah, certainly. Actually, I can talk about both the circular and the min-max tool. So there is software that we presently have on the website that generate those things, but our intention is to actually not migrate those over when we switch our web platforms later on this year. So They have effectively been discontinued because they required a lot of staff time to actually maintain and generate the data that's required for those. So I would like to second Mike's comment earlier that the AAVSO target tool is probably going to be the way to go in the future. And we have plans in 2025 to significantly enhance VSX so that the things that were provided by the min-max tool and the most of the content that were in the LPV circular, for example, will actually be something that you can just go and search for, give me all the LPVs from VSX and get the same data relatively easily. So, but that won't come out until 2025, probably near the tail end of 2025.
One brief comment, Brian, and to everybody is, I also find VSX to be very, very valuable as to a star's behavior, what is it doing now, and so on. VSX, use that for your stars of interest. And secondly, use the light curve generator. Everything you know in graphical and tabular form that the LPV circular and so on used to present or is done much, much better in the light curve generator. Who observed the star conditions, behavior? I mean, it's all in that. So that's what I recommend. And I will henceforth turn it over and be quiet for once.
Okay, thanks so much, Mike, and thanks, Brian, for the context. That did run a little bit long, but fortunately we do have some minutes of grace built into each time slot on this agenda. So, all right, and with that, I would like to hand the floor over to Kevin Alton, who is the leader of the Eclipsing Binaries section.
Okay, good day. Guten Abend. Bonjour. Buenos dias. Dobre dzień. I'm presenting the slide deck from the Eclipsing Binary section today. Apparently, the Eclipsing Binary section is one of the oldest within the AAVSO. We have not had any webinars until most recently, but we're planning on doing them quarterly. If you have particular interest in eclipsing binaries, this is the website you should be looking at. There's a lot of detail in there that I simply won't have time to go over today. But again, if you're interested, I would strongly suggest that you go to this URL. The goals of the Eclipsing Binary section is to provide background information about eclipsing binary star systems, to provide mentorship for those individuals interested in studying EB systems, either through the EB forum, which Mike strongly suggested, as well as potentially if you're interested in EB or in photometry or whatever, to formally assign a mentor, of which I am for both eclipsing binaries as well as for photometry, and to encourage active participation in study of EB systems, quarterly section meetings to discuss EB-related topics, to propose potentially an annual EB section project and assign interested participants, hands-on photometry, data mining, and then potentially even publishing results in the JAVSO. By background, my background is in classical chemistry, physics, and my graduate degree is in analytical chemistry. I spent over 40 years in the pharmaceutical sector as a senior research director. And when I retired back in 2010, I decided that I would make use of my physics background and to get more heavily involved in actually doing research on variable stars, not just eclipsing binary, but also short period pulsators. I'm more into immediate gratification than the LPV folks are. As such, I also have two observatories. I have one in my backyard in northern New Jersey, which I unfortunately don't get a lot of use out of because weather in Jersey is just simply not amenable to frequent observing due to cloud cover. I have a remote observatory which I operate through a web browser in Arizona, and that's where most of the research that I'm doing is centered. A little bit about eclipsing binaries. Binaries and higher order systems are actually very common, representing more than half of stars greater than one solar mass. That number may actually be closer to 60 to 65% based on some recent surveys. Observing the eclipse of a binary star by whatever means is a matter of perspective, which depends heavily on the observer's angular position. If the line of sight and the orbital inclination of the binary pair is around 80 degrees or higher, then a total eclipse may be observed. And I'm going to mention, I'll continue to mention total eclipse, which is really critical to doing any modeling of the data. As you can see in this stacked slides, when the orbital inclination is 90 degrees, the eclipse is total. Whereas as you get down to around 75 degrees, the eclipse is not total. This is the territory that we want to be in, that area where, and there are exceptions where you're at least 80 degrees. Detection of stellar variability has traditionally been done visually. In fact, the vast majority of data that were collected over the last 100, 150 years is visual. Only since the turn of the century has more accurate data been able to be generated either using photography or photometry. And that could either be by photoelectric means, by CCD, charge coupled devices, and CMOS, which is the most recent mode of detection for stellar variability. Now, there are a number of different ways of detecting binarity, other than through visual or through photometric means. The most important is what's called the radial velocity method. Stars technically don't circle each other, but rather each orbit a gravitational balancing point called the barycenter. The simplest case assumes circular orbit, and this relationship of mass and distance is absolutely critical. It's sort of like a heavy kid and a light small child being on a teeter-totter, that if you want to balance it out, you've got to put the lightest kid on the furthest from the barycenter. In the radial velocity method, with a less massive binary partner, we would see a slight wobble of a massive primary star, which is indicated on the top here. However, a more massive stellar companion, the same distance, would place the barycenter farther out and lead to a more discernible motion of the primary star. This is usually detected using spectrographic means or the radial velocity experiment. And in the end, the amount of wobble is going to be directly related to the or measurable as the velocity k, all of which can eventually lead to understanding what the mass ratio is, as well as the sum of the masses. These two are important constraints if you want to model the binary systems using the Wilson-Diviney code. This is an example of a plot from a double line spectrum for the algal type eclipsing binary V 1241 tori that we published back in 2023. And you can see that the K2 K1 ratio is in fact the mass ratio. There's also means of detecting a binarity using direct imaging, which, however, requires extremely high angular resolution, generally adaptive optics for ground-based systems, or with satellite telescopes like the James Webb. They can usually, interestingly, use an umbrella to block bright stars, because their comparison may be between a very bright star and a very faint star. And then also interferometry. You can see down here, algo A and algo B. Actually, you can observe the orbit of that system. Eclipsing binaries come in various types. One which is fully detached, which means they're in no way connected. Generally, these will have an orbital period which is measured in many days. Now, again, once we start talking about stars that fill their Roche lobes, things begin to change considerably in terms of the shape of these curves. This is so-called semi-detached, which is an algo type, which typified by algo type systems. These can be in measured in days and some in less than 1 day. Then we get to the contact types, in which the Roche lobes are actually in slight contact with one another. You can see how the light curves tend to be more continuous. And then the last kind, which I've done most of my research on, are so-called over contacts, or the UMA type. And many of these have orbital periods less than 1 day, which make them great candidates for photometric light curve study. So what do we need to do to collect eclipsing binary light curve? Precise time series image acquisition may last many hours, so that guiding is strongly encouraged. If the ultimate goal is to model and publish the results, then you really need to use standardized photometric filters such as the Johnson-Cousins or Sloan's.
Kevin, you've got about 2 minutes.
Okay, science images should be calibrated, dark and flat corrected, and the calibrated image should be registered or plate solved and reduced to time versus brightness, a standard either baryocentric Julian date, or heliocentric Julian date. There are a number of different light curve modeling software options out there. One is Binary Maker 3. It's a really good starting point for someone not experienced in modeling light curve data. The only limitations is that there is no provision for simultaneous solutions for multi-bandpass light curves, nor is there any determination of uncertainty estimates for model parameters. I've used Phoebe 0.31a over the last 10 or 15 years. It's a bit dated. It's being replaced now with Phoebe 2, which I have not even tried, and it uses differential corrections to optimize the light curve fit. And then finally, WDWINT 56A, which is a software tool developed by Bob Nelson, which uses the same Wilson-Diviney code as Phoebe. And what's good about it is that it does provide for uncertainty estimates for all model parameters, including the spots, which is really important for publication purposes. The last thing that you'll want to look at with eclipsing binary systems is to be able to determine whether there are any secular changes in the orbital period. And some of these can be detected in less than a few decades, so that accurate and precise times of minimum are required. Herein, there are a number of different ways of determining those times of minimum. A very a powerful tool is Parenzo 3, the most recent version of Parenzo. And in some cases, specialized fits using Mathka, which was published by some Ukrainian folks. Here's an example of the polynomial fit of a light curve using Mathka. And here, where you have a very flat bottom, the wall-supported line model does a really good job of fitting the data here. I would strongly encourage that people give this program a try. So in the end, secular analysis can tell you whether or not you have no apparent change in the orbital period, which would be a sort of a linear straight line relationship. If you've got a polynomial fit, then the chances are there is some sort of a change in time which is directly related to the quadratic coefficient. In this case, the orbital period is changed by a fixed amount, and for this example, was minus 0.0358 seconds per year. Not a whole lot. That's pretty typical. And then more complicated ones, in which you may have a parabolic fit in addition to an underlying sinusoidal change. And in this case, that may be due to either a gravitationally bound third body or the Applegate effect, which are periodic changes in the gravitational quadrupole due to magnetic torque, basically star spot activity. And this can be energetically assessed using this paper by Volschau. If you're interested in learning a bit more about the research that I've been doing, you can go out to my my website, underoakobservatory.com. I have all of my more recent publications there, as well as spectra from a number of extended objects as well as stars. Here I am with my backyard, and here is the site manager out in Benson at our observatory called Desert Blooms. All right, I appreciate your time and hope that I have encouraged or enticed you to consider eclipsing binaries as objects of interest for you. Thank you very much.
Excellent. Thank you, Kevin. Very interesting stuff. Okay, so next up, we are going to be hearing from Kris Larsen, the leader of the AAVSO's solar section. Kris, take it away.
Thank you. And hopefully you are seeing my screen. Okay. Yes?
Looks great.
Awesome. So the few, the proud, the solar observers, we observe one star once a day, but we get to sleep at night. So here's our serious disclaimer that we can help you to observe safely, but in the end, you are responsible for your own safety in looking at the sun, not the AAVSO, not me, not the solar section, and not the manufacturer of your equipment. Please check the safety of your equipment before every observation. So the question is, why should you observe the sun, other than, of course, the total solar eclipse? Well, we got a really good idea about why about 3 weeks ago. there was a very large sunspot group, and it generated a tremendous amount of interaction between the sun and the Earth. It threw out flares and coronal mass ejections and generated a giant geomagnetic storm, which resulted in aurora seen everywhere except where I happened to be at Kalamazoo, Michigan at a conference. So a quick introduction to solar observing. There are two different ways that you can safely look at the sun. You can use what we call projection, which is projecting the sun's image on a screen through your telescope, or you can use a filter that goes over the front, over the aperture. Do not put a filter on your eyepiece. They were selling those in the 1970s, and some people went blind because they failed. If you use a filter, it goes on the business end, the front end of the telescope, to prevent the light from entering in the first place. We have about 70 observers that observe. About half use projection and about half use the filter. So people ask, well, how am I going to, point my telescope at the sun without a finder scope? It's actually really easy. All you need to do is align to the shadow of your telescope. Assuming you have a circular tube, cylindrical tube, you just look for the shadow to be a perfect circle, and you know that you are perfectly aligned. Do not be this guy over here and try to use a finder scope to look at the sun. In fact, I have permanently removed and subsequently lost the finder scope for the scope that I use to look at the sun. Now, what do? We don't just count sunspots. We measure what's called the Wolf number. And this was first developed by Rudolf Wolf at the Zurich Observatory in 1848. We are looking for areas of activity on the photosphere, the sun's visible surface. Even if it's an isolated spot, that is an area, a unique area of activity on the sun, and it is important. Now, the number of individual spots within a group is also useful information, so we measure both. We try to get the number of groups, the number of active regions, and then the total number of spots within all of those regions. And because the number of groups or active areas is more important, we weight it by a factor of 10. So the Wolf number is the number of active regions or groups multiplied by a weighting factor of 10 plus the overall number of spots. An isolated spot, again, counts not only towards your S or spot value, but if it's an isolated area of activity, it also counts as a group. Now, for the AAVSO American Relative Sunspot Number, what we do is there is a magic crystal ball. No, actually, there is a statistical analysis done looking at observers, because everyone's eyes are different, everyone's instrumentation is different, everyone's weather conditions are different, and so on and so on. And at headquarters, you don't do this, we give you what we call a K factor, the reduction coefficient, which takes into account the differences between observers. After you've submitted 100 observations, you get your own shiny K factor. Now, what's actually going on here? The sun, being a hot ball of plasma, actually rotates at different speeds in different latitudes, at least the outer third of it does. And what that does is it tangles up the sun's magnetic field lines. And that's what actually generates sunspot activity. Every 11 years, about every 11 years, the sunspot's magnetic field is so tangled that it literally snaps, resets, and the process starts all over again. And this leads to the sunspot cycle. The average is 11 years, can be as little as 7 and as much as 17. Notice that the height or amplitude of maximum is very, very different. The sun is different in brightness by a very, very tiny amount, a fraction of a %. So that is not what is generating climate change. But it is important to understand the sun's magnetic field that we understand the solar cycle. So the sun is considered a rotational variable and a spotted star, having two cycles. One, the approximate 11-year cycle of the sunspot activity, and the rotational cycle, which is about a month, 27 days at the equator, about 33 days near the poles. Now, our ability to predict future sunspot activity is not so good. We are currently in sunspot cycle 25. That's only 25 well-measured cycles of activity. That is not enough to get a pattern when the pattern is nowhere near perfect. Now, people will sometimes say, well, why can't I just pull up a picture from the internet and count the spots? Or why can't I just take a picture? The importance here is consistency. We want to measure sunspot activity using the same technique over decades. And that's what we've been doing at the AAVSO since World War II. That is how we can aggregate our data and make it scientifically useful. So to get started, I invite you to go to the website for the solar section. I am again a co-leader along with my partners in crime, Rodney Howe and Kim Hay, who was on the call. Hopefully she's still here. We have a lot of information that you can check us out. If you're interested in the impact of solar activity on our atmosphere, I invite you to look at the materials for the solar sudden ionospheric disturbances, or SIDS. We can actually show you how you can build an antenna and you can actually measure changes to the ionosphere due to solar activity. One of the places to start is, of course, with our solar observing guide. It is available in multiple languages. And we have our own software for uploading your observations. We have what's called the Sun Entry software. You can download that from the AAVSO website, and you put in your AAVSO observer code, your username, and a password, and it will actually calculate the wolf number for you. You don't have to do 10G plus S. It does it for you. It's actually very simple. You can use the same AAVSO observer code that you use for your nighttime observations for your daytime observations. Every month, we aggregate the data. We write about some solar items of interest and publish the solar bulletin. And you can actually see your data and you can compare it to the data of other people and you can see how you're doing. And I just submitted my 1476th observation, I think, so I'm chasing 1500, hope to get there this summer. So, your personal checklist for becoming one of the solar observers. Go to the AAVSO Solar Section website. Read the observing manual in the language of your choice. Make sure you have proper equipment. Get an AAVSO observer code if you don't already have one. And when you upload your observations, you will download the Sun Entry software from the website. And I invite you to email us at solar@aavso.org to introduce yourself to the solar team, ask any questions you might have, and you can also join the Solar Observing Forum on the AAVSO website. So it's fun. If it's done correctly, it's safe. And I invite you all to become one of the special daylight people.
Wow, fantastic presentation, Kris. Excellent, thank you. So I see that our first question here for the Q&A actually is addressed to you, Kris. And this one asks, how far apart should sunspots be in order to be considered separate groups? Or if the criterion isn't distance, then how do you determine whether sunspots are in the same group or in different groups?
That is where experience comes in. It is part science, part art, part experience. I know that when I first started out, I was breaking things into too many groups because I would go back and look every month, and we actually published the raw data. And so I could compare my data with the average of all of the solar observers, and my number was always higher by like 10 or 20. So I had like 1 or 2 extra groups that I was dividing things into. Generally speaking, spots within a single group, in the group itself, the spots are more or less parallel to the equator. Now there's something called Joy's law, and it turns out that they're a little tilted towards the equator, but more or less, you don't see, like this. It's pretty much parallel to the equator.
Mhm.
And so what we do is, if you watch the sun often enough, the groups, because they typically last for days, weeks, or even months, that group that created the aurora last month has now gone all the way around the sun and popped out again on the other side going, hi, still active, here's a flare. So you watch the evolution of groups, and that way you'll notice that, oh, this other thing happened over here. That's far enough away and it's different in latitude. That's something else that's brewing. And sometimes when I'm doing notes in my logbook, I'll make a question, not sure if this is another group. And then the next time I see that, either the next day or 2 days later, I look at it and I go, oh yeah, that's something new that popped up. Or nope, that was just part of this other thing that's just evolving.
Okay. Great answer. Thank you. Okay. Our next question here, this one is directed towards Kevin. So what are some considerations if you wanted to use AAVSO net to observe eclipsing binaries? What should you keep in mind?
Well, from what I understand, you would have to sort of write a proposal for, what you're planning on doing, in order to get enough time, to, fully, I'm assuming you'd want to generate a full light curve. I haven't actually used that facility myself, since I have, my own observatories for doing things, but I would assume it would have to be reviewed. The research proposal would have to be reviewed, and again, I think you probably would have to go after eclipsing binaries that have relatively short orbital periods in order to be able to collect a maximum amount of the light curve in a minimum amount of time.
That makes sense. And adding to that, I know that AAVSO net traditionally is more of a one look per night type program. You might get a sample of 15 minutes and then get that a couple times per week for several weeks is how most programs tend to run. I think they can also accommodate one single night time series, but most tend to run with that more scattered cadence. Kevin, can you observe eclipsing binaries with a more spaced out cadence like that?
Yes, you can, but it will take you a considerable amount of time to get a full light curve if that's your goal. I mean, for instance, um, if you're looking at something, let's say with less than a half a day orbital period, you could, if you were given unlimited amount of time, you could probably do that in a couple of days. Whereas if you're doing scattered sampling, then might take you weeks or even potentially months to get a full light curve. The other thing is you need to be careful with biases. For instance, if you had an orbital period of 1.0 days, it might take you forever to get a full light curve, or a half a day or a quarter of a day. So you need to be wary of those challenges when you have exact multiples of one.
Mm-hmm. Makes sense. Okay, thank you. All right, our next question here is addressed to Mike. So Mike, in your presentation, you had mentioned that there was an interesting theory that the double dip appearance in some long period variables light curves might be due to chaos dynamics. Could you take about a minute and just elaborate a little more on that?
Well, this is easy where I can be succinct because I know almost nothing about the chaos theory. I think it's related to phenomena that have been theorized that the dips or the alternating minima are due to colliding shock waves. You have an outward propagating shock wave, part of the pulsation, but the outer layers are coming back in. And people have tried to use chaos theory to model that. I don't know how much it tells you about physically what's happening in the interior. So unfortunately, I am not knowledgeable on that.
Okay. Well, thanks anyway. That still helps. Okay. So our next question is going back to the solar section. So Kris, can you use any telescope as long as it has a proper solar filter, or do you need a special type of telescope?
Short answer is we prefer smaller telescopes. I would not tell Mario to use his 0.8 meter to look at the sun for a number of reasons. For starting forest fires. You don't need a big aperture because again, we're trying to compare apples to apples. And so we know that backyard apertures have, there's been a inflation factor, shall we say, with people getting bigger and bigger telescopes. And so smaller telescopes or stopping down the aperture of your telescope is great. If you are using a solar filter, obviously the cost of your filter will, be determined by the aperture. So that's one reason to use a smaller telescope. If you are using projection, you definitely do not want a large aperture telescope because think about how much light you are bringing into your telescope and you can actually damage your eyepieces. This is not something where you want to use your naglers, okay? So smaller aperture, especially if you're using projection. Also, if you are using projection, do not use a catadioptric telescope because the heat buildup inside that closed tube can damage your telescope. So the one reason why I have only used filter my entire career, I've been observing the sun since like 1989, 1990, is I want to protect both my telescope and myself. And the filter protects my telescope. Obviously, projection would completely protect your eyes, but I've done this long enough. I trust my equipment. I test my equipment every time. I know how to safely observe the sun. And if I've been doing it for that long and I can still see, it tells you that you can observe the sun safely.
Okay, thank you. And I'd like to add a follow-up question onto that one. You mentioned that you test your equipment every time. How do you do that?
I'll show you. Very simply. Here is my solar filter, which I keep safely and double bagged. And it will remind you of a mirror because it reflects 99.99 something percent of the sunlight. You want to visually inspect it. Make sure there are no obvious flaws, cracks, spots, anything. And you don't clean it. Don't touch the coating, okay? So you look at it and you go, okay, everything looks great. Then what I do is I go outside and I look at the sun through it with just my eyes. If I see any bright spots, I know that there is a defect in the coating. And then I put it on my telescope, make sure I put it on firmly, make sure it's on, when you're putting it on, it's pointed away from the sun, obviously. Then I do the alignment with the shadow. Again, I'm not looking at the sun. And then once I have it pointed at the sun, I look through the eyepiece holder without the eyepiece, because again, that would be an unfocused image of the sun, and heaven forbid something was wrong, I would at least not be looking at a focused image of the sun.
Okay, thank you. I appreciate you sharing that. Okay, so our next question here is going back to Kevin. So this question asks, how often are eclipsing binaries observed in cases where you can see one entire rotation of the system in only one session. I guess a different way to phrase that is, how many eclipsing binaries are there really that it's possible to observe in one night?
Unfortunately, not a lot, and those that meet that criteria have been investigated many times. What comes to mind is one is CC-COM, which I think has a rotational or a orbital period of around 0.22 days. So that in one session, you probably can, a good long session, you can probably get an entire light curve. So that being the case, CC-COM has been observed many times. There's lots of data for that particular system. The ones that again have limited amount of data are those that are multiples, those 0.25 days, 0.5 days, 1.0 days. Those are good targets if you've got a global community to take a look at them, because from your vantage point, you're going to be seeing the same part of the light curve day after day after day after day if it's 1.0. Whereas if you've got somebody in Belarus or somebody in China or Japan, they're going to see a different part of the light curve. And if you can pull all those light curves together, then you can get a full light curve.
Okay.
Yeah. Not that is part of our discussion here, but high amplitude delta Scuddies are really good targets for short period light curves, because in those cases you can have pulsation periods that are less than 0.1 day, and easily within a few hours you can get a full light curve.
That's a great point. Yeah. The SPP section, I have to stick this in now. The SPP section will be presenting on June 22nd, and they'll be talking about high amplitude delta Scuddies at least a little bit, I'm sure. So
Yeah, as a mentor for photometry, those are usually the first targets that I have people go after, because they're the easiest to get full light curves from. And they're relatively easy to analyze too, to light curve model using discrete Fourier transform.
cool. All right. Okay. Let's see. I see we have a comment which came in just related to the last question on short period eclipsing binaries. Someone's mentioned that W Ursa Majoris has a rotation period of roughly 8 hours. So thank you for sharing that. Okay. Now our next question is directed at Kris. So Kris, you had mentioned that the sun is a rotational variable. If presumably if we were looking at it in a different way from a distance and doing photometry on it, we'd be seeing its light output fluctuate. How does it compare to the type of rotational variables that we study in other parts of the AAVSO? Is it pretty similar to like the RS stars, or is this a whole different class?
It would be similar to what we would call the closest thing I can refer to as a BY Draconis star, although those are normally red dwarfs and they have much larger variations. In terms of the percentage of light that is blocked, we're talking, exoplanet type, if you figure that a large sunspot group blocks about as terms of volume or surface area, about as much as maybe the planet Saturn. Okay. Now, of course, a sunspot is not completely black, so the analogy is not perfect, but we're talking very, very tiny changes. But we have been able to see comparable changes in sun-like stars. However, in viewing changes in the magnetic changes in sun-like stars, we can also use other proxies. We can use spectroscopic, this is near and dear to your heart. We can use spectroscopic changes. We can, for example, we can measure the brightness using calcium lines in particular. So there are, if there were extraterrestrials monitoring the sun with sufficient technology, they could tell that it was a variable star, but it would not be one of the ones that they would be training people on in their version of the AAVSO, because the changes are microscopic.
Got it. Thank you. Okay. And I think that Brian has a follow-up question. Brian, would you like to come off mute?
Yeah, so first off, Kris, would that be the Alien Association of Variable Star Observers?
You can go ahead. We can might as well use it if we're going to change the A, right?
Yeah, so I couldn't resist that opportunity. So so Kris, in addition to the visual observations of the sun, the solar section also has other data that it collects, right? There's the SIDS group as well.
Right, yeah. To keep within my 10 minutes, I just very briefly mentioned the SIDS. SIDS is the sudden ionospheric disturbances, and that's basically how space weather, how these solar storms, which are intimately related to sunspot activity, affect the Earth's atmosphere, in particular affect the transmission of radio signals in our atmosphere. And so people can, using plans that they find online or on our website, they can build antennas, which don't cost a lot to build. And then there are certain radio stations around the world that you can tune in, and you can basically, it's the attenuation of the signal, and you can use that to show when there are disturbances. And that data is also data-based and is published in our monthly solar bulletin.
I remember when I first met Rodney Howe back in 2006. He's the co-section lead along with Kris. He was doing radio astronomy, and he told me about the SIDS back in the day. So it's you know, if you don't if you don't like looking at stars, you don't like looking at the sun with your eyes, you can look at how the atmosphere is impacted using you know, radio reception instead. So that's a fun program as well.
Very cool. All right. So we're down to our last couple of questions here. It looks like the next one is addressed towards Kevin. So, Kevin, during your talk, you mentioned the over-contact systems. What is the end state of those systems? Are they stable? On what time periods are they stable? What can we expect to happen to them in the future?
There are a variety of theories that cover that. Some suggest that that collapse is inevitable, and that they will merge into a single star, and others suggest that they're on the way out, that they're actually separating. I think most of the people probably believe that collapse is inevitable and that they will merge as a single star. But we're talking over billions of years.
Okay, thank you. Okay, and we have one more here for Kris. This came from one of our viewers on Facebook. So this person is asking, how frequently should you make your solar observations? You know, what's the ideal cadence?
The ideal cadence is really easy. Every day, once a day. Now, again, to keep things as equal as possible, doing it about the same time every day is preferable, because that way the sun, I mean, there are seasonal variations, obviously, but roughly, you know, same sort of just, you know, height above the horizon. I tend to do mine because the observing platform that is attached to my office on the roof here basically faces east. So I do my observations usually between 9 and 11 in the morning. I don't have to, but it's easiest for me, and I know that my data is going to be at least have some consistency in that way. But and once a day, every clear day. And again, everybody's different. Last month, I actually got 15 observations in, which is a lot for me, given my life and my conditions here. There are months where I've had 2, but 2 is better than 0. So however many You can contribute. Every observation is valued. Every observation is loved.
Absolutely. Wonderful. Thank you. Okay. And I believe our last question here is for Mike. So Mike, would you mind just sharing a little bit about if there's any particular star which you are either focusing on yourself right now, or which you'd particularly like to see people start studying in greater detail, one with something interesting going on and we just need more data on it?
Well, that's a nice wide open question. I don't have any one particular individual star. When I observe LPVs, I mentioned during my talk that I was particularly fond of RV Tauri stars. And I don't have any particular favorite within them in that class. Someone asked earlier about the chaos theory or the reason why we have the alternating minima in these stars. To make it more interesting, more complicated, initially it was thought that these stars were actually binaries. And so you're actually seeing an eclipsing effect when you get to the deep minima, as opposed to the shallow minima, that the companion star is elsewhere. It's not in the line of sight. And then it became rather obvious that that wasn't quite the case. But just to complicate things, there is a subclass of RV Tauri stars that are thought to be in binary mode, and that they eclipses do affect the light curves. But as you observe more and more, you realize that again, it's not really just a binary effect, an eclipsing binary. But I have no particular favorite. I think they're all interesting. And I would really encourage anybody to get out and observe RV Tauri stars. Their periods are typically 50 to maybe 120 days, to pick a couple of numbers. So in that sense, there's a little more going on. You can see more changes more rapidly if you're an individual observer. My interest in these stars is these are in the instability strip while these stars are on what we call the asymptotic giant branch. So these things are pretty highly evolved. They used to be red giants and probably Myra-type variables, but as they've evolved, they've skipped over to what's called the AGB. And as they evolve over there, they're also in what we call the Cepheid instability strip. But they're not Cepheids as such. But they're way up there on the way to becoming white dwarf stars. What will happen is they'll get to a point, they're shedding mass like crazy. And that mass being blown off will lead to the precursor of a white dwarf. So you're really seeing a star in a very late stage of evolution just before it wanders off to the hot end of the HR diagram to ultimately become a white dwarf. So that's something to keep in mind. A simple answer, though, after all that, I don't have a particular favorite. I have a favorite class, and that's the RV Tauris. Related to the RV Tauris, we think are what are called the yellow semi-regular stars. These stars don't have an organized periodicity, but I can tell you from my own observations, I've observed some that are classified as semi-regular yellow giants, but actually they're looking a little bit like RV Tauri stars. So there seems to be an evolutionary connection. If you're one of these do-it-yourself go-getters, observe both the yellow semi-regulars and the RV Tauris. Ultimately, what the goal is, are we seeing an evolutionary path of one type of star being variable as it transitions to another that might be more organized, like an RV-Tari. Long answer, but I probably didn't. I probably can't give you a favorite to
Mhm.
pick, but many of them are rather bright. You don't need to do CCD photometry. They are also usually pretty well suited to visual observations. There are
Right.
quite a few that are bright enough. That's it.
Very interesting. All right, I might have to add some RV-Taris to my binocular program. Thank you.
You can see a number of them with binoculars. They're
Nice.
they're bright enough and good for visual.
Nice. All right. So, while you were giving that answer, we did have one more question sneak in, and technically we've got about 2 minutes left in Q&A, so I think I'll go ahead and read this out. This is addressed to you, Kevin. So this comes from Sam Lee, who asks, for the eclipse timing variations that you talked about earlier, is this for multi-star systems, like more than 2 stars, or is this for binary systems with orbital instability?
Well, actually, it would be all of the above. I gave an example of a situation where there probably was it was a trinary system. So if you've got enough data over a long enough period of time, if you had a trinary system, you should probably be able to see the wobble, this sort of sinusoidal variation in the eclipsing time curve to be able to actually determine its periodicity also.
Mhm.
So it could be a binary system, or it could be trinary, or for that matter, I've seen data on quaternary systems that were you could parse out the sinusoidal undulations that these secular curves can observe can determine.
Interesting. Thank you. Okay,
I have
and
a question for Kris.
go ahead.
Has software-driven uh, pattern recognition or AI software proven to be helpful to get that K correction factor equal to 1?
Well, I don't know that you want it equal to any particular number. You're not trying to drive it to any number. What you're doing is for each person, you are trying to compare them to the statistical average.
Right.
And we at the AAVSO use, I believe, Harlow Shapley's methodology, which has been looked at a number of times. If you go to the JAVSO, you will find a number of papers on the K factor. You can just search for K factor. Grant Foster took a look at it, and a bunch of other people. And so again, we're trying to compare apples to apples, how we're observing today to what was done going back to the 1940s.
Yeah.
So I don't know that I am not a statistical wonk, so I'm not the person to ask this question to, but my gut is telling me that I don't know that is going to give us more, that is going to impact our data in a way that makes it more consistent or more scientifically useful. I could be wrong, but
Yeah, I mean, an
my gut.
analogous situation is, of course, much of the times to minimum data that were generated, since the turn of the century, were done visually, and they're plus or minus a minute, or plus or minus 2 or 3 minutes, whereas modern values that are collected using photometric methods are literally plus or minus seconds. And there is if you're doing secular analysis, there are many times when I've had to ignore the visual data because they just simply don't fit the data that were collected over the last 20 to 30 years using more accurate methods. You don't see that being an issue in the future with sunspot data where comparing the two actually become apples and oranges?
As long as we continue to observe the sun using the same methods that we've been using since the 1940s, our data will hopefully remain consistent. And that is why we continue to look at it. And just to give you an idea, there are, again, the Zurich number and other numbers. And a number of years ago, groups, Rodney can give you the actual data on the groups because he worked with them. They looked at all these different sources of sunspot data and looked at all of them and looked at the internal consistency and looked at, by sort of scaffolding these different data sets with each other, they reevaluated the overall, going back again, only at that point, 24 cycles of solar observation, and we're able to recalibrate that data a bit. So the fact that they could still compare, even from different data sources, from different observer sources, this data in a scientifically useful way. In the case of the Zurich data, going back to the mid-1800s, tells you that there's value in how solar observers are using sort of old-fashioned methodologies so that we can continue to compare apples to apples and have scientifically relevant data for the historical record.
Okay, thanks.
Well said. Thank you. Okay, and with that, that brings our Q&A to a close. So before I put up these end slides, I'd just like to remind everyone that the wonderful presenters that you've just heard from are all leaders of AAVSO sections or special interest groups, and they are looking for participants to join them and do this sort of work in their sections to learn more about these types of stars and to advance science. So if you are interested in becoming involved in any of this work that you've heard about, here's what you should do. Go to our website, that's aavso.org. If you scroll down a little bit, you'll see an icon that says something about observing sections. Click on that. You'll get a whole list of all of our sections, all of our special interest groups. Pick the one that's interesting to you and reach out to the leaders of that group, okay? You can reach out to the people who you've just heard from today and let them know that you're interested in participating. And it could be the start of something wonderful. All right. Now, before we close out, I would like to extend a heartfelt thank you to Kris, to Mike, and to Kevin for joining us today and introducing us to your sections. Thank you. This has been wonderful.
Thank you.
Thank you. You're more than welcome.
Right. I would also like to thank again this webinar sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. And quick reminder, this was the start of a magnificent mini-series, which we're running all this month. Our next webinar will be next Saturday, and it will feature the exoplanet section, the YSO or Young Stellar Objects section, and the I&E or Instrumentation and Equipment section. We'll hear from all three of those leaders about the sort of stuff that their sections are getting up to and how you can get involved in those. If you'd like to learn more about the webinar, or if you're ready to sign up, go ahead and visit aavso.org/webinars. I hope to see you there. And now I would just like to say thank you. You, all of you out there in the audience. I know I say this a lot, but it's true. It's your participation in our webinar series and in the rest of our programs, which allows us to keep growing, to keep educating, and to keep making an impact on variable star science. So, thank you. We are so grateful for your support.
Indeed.
today's broadcast has been recorded, and if you'd like to go back and reference any of the information from the presentations, you can do so on our Facebook page where the recording is automatically archived. So just as soon as I hit the stop button, you can find it there. We'll also upload the recording pretty soon to our YouTube channel, where it will join an enormous library of educational videos, stretching back through years of this webinar series. You can even find some presentations from the sections last year when we did a different series on them. To find our library on YouTube, just visit the YouTube website and search for AAVSO HQ. That's the name of our channel. Alrighty, now when you log out of the webinar today, you should be automatically shown a survey. I'd really appreciate it if you could fill the survey out. Let us know what you thought about today's webinar and your suggestions for what we might be able to do different next time. I'm looking forward to hearing from you.
Bye.
Now, to close, I'd like to extend one last huge thank you to Kevin, to Mike, and to Kris for your excellent presentations today and for all of the work which you do in leading your sections. Thank you. We really appreciate you. And with that, I'll see you all
Have a
next.
good day, everyone.
Yeah, have a good weekend, everybody.